Hi, let's get started. I've got two videos for you today, and I don't know how many times I've shown this before, but take a watch. I'm going to get things started. Jot down anything you think is important from these videos. I don't know how many times I've shown magnesium. It's got to be at least once, but maybe 0 times, and if that is the case, I'm really sorry. But this is magnesium, fairly common, fairly accessible in the chem lab. And you can see somewhat chemically reactive. Well, that certainly took a while. Oh, yeah. So that's your characteristic magnesium burning video. Very, very bright white light. It was used in older flash bulbs, like the single-use flash bulbs. You can see why. But it also gets interesting to take a look at a second reaction that occurs.
I want to show you a reaction which I didn't know could occur, the reaction between magnesium and water. The reason why I didn't know it can occur is quite simple. Let's look at this experiment. Here I've got a piece of magnesium ribbon and some water. You see that if I add the water, absolutely nothing happens. I didn't really think whether magnesium could react with water. However, Neil has done some quite exciting experiments which Brady has videoed in slow motion. So what Neil did was to take bits of magnesium, set fire to them in air, so they were burning really brightly,
like the other
and
video.
then gently lower them into a large container of water. As with all his experiments, he began on quite a small scale.
He throws it.
In the first experiment, it's all quite dark. You can't see the water very well at all, but you can see the magnesium as it comes in. What I found really quite surprising is that the burning magnesium continues to burn underwater. In fact, bits of it start coming out of the water again, breaking off. And that came to me as a real surprise to begin with. But then I realized that the magnesium is pretty hot, close to its melting point. Its melting point is only 650 degrees centigrade. And in fact, in some of the shots you can see bits dropping off the magnesium even before it gets to the water because it's melting.
That's going to look good in slow motion.
You have a very clean surface of magnesium. And so there is no oxide layer to protect the magnesium as there is in the water that we've got here, where the magnesium is coated in a layer of oxide. So it's insulated, if you like, from the water. So you have very high temperature water and clean magnesium, and so you can get a reaction of magnesium producing magnesium oxide and hydrogen. It may be magnesium hydroxide, but you will get hydrogen. So you have an exothermic reaction making the magnesium oxide or hydroxide, and you're producing hydrogen, which itself can burn and could cause a minor explosion.
That's probably a good place to stop things. I'll put a link to this video in the description if you want to go back and watch it yourself. But yeah, this is a demonstration. This is something that students get to carry out. We have big ribbons and we'll give them to students in person. So if you've been in a chem lab in the last year, you probably have carried this out, or you've at least seen it. But the big question I want to take a look at today is not what happens when you do burn magnesium. If such a reaction occurs, he said it in the video, Professor Polyakov said it in the video, it's exothermic, right? So where we've been so far in this energy discussion is that energy and stability have this relationship to them. So the way I feel like it's easiest to communicate is that there's this driving force in nature, in the universe, where reactions will end up going in a typical fashion to make more stable products, and almost always this will yield exothermic processes. Do endothermic processes happen? Absolutely. So this is, of course, an oversimplification, but a decent rule is to say that exothermic reactions are usually what happen. And when exothermic reaction happens, you have that negative delta H. But this scratches at an interesting topic. If exothermic reactions are the way that nature goes, and wood reacting with oxygen, or something like magnesium reacting with oxygen, are exothermic processes, both of them, why do you ever see reactants? Why do they exist, right? When you have a match, you have the wood, and you're in an oxygen atmosphere. So why does wood ever exist if the exothermic direction is the way nature goes? And to really get into this, you kind of have to talk about the nature of chemical reactions as a whole, which it's a very large discussion, but I'll try and boil it down. We've discussed enthalpy as this certain way of measuring the total energy content of the system. It's almost more beneficial to think of it as a label of the energy associated with how that matter is constructed in that situation. One second. Sorry, I had to let the dog out. She was barking. Don't know if you heard that. The arrangement of these molecules is way more subject to fluctuation than I have let on in these videos. As you can see in this picture, these atoms don't stay still. In the solid phase, we say the particles vibrate, but even within a molecule, things are not nearly as rigid as they made them out to be, where you have these tetrahedrons and trigonal planars and linear molecules. It's really more like you've got a group of wibbly-wobbly proton-electron attraction springy things. And specifically, those springs, if you want to think of a shared pair of electrons as kind of like this bouncy, attractive thing, can be stretched. When energy is given to a particle, a molecule, an atom, one of the things that can happen is things start bouncing around. So in much the same way as we saw when solid became liquid, and the solid particles were vibrating in place and eventually started moving quickly enough to break free of their intermolecular forces. Sorry, space, definitely tight. I think 10 was a good one. Even within the molecules, given more energy, the particles themselves can start to vibrate, and that will stretch and pull on the bonds themselves and make them loosen up. And when that happens, that's when you start to get situations where one bond gets stretched, and if another particle is approaching your molecule, you can start to make a new bond as the old bond is being stretched, and you almost kind of snap one rubber band as a new rubber band is being put on. And so to get a chemical reaction to happen, a lot of times some sort of energy is needed to initiate or activate the process, called an activation energy. You saw the magnesium sitting in water, no reaction. You saw the magnesium hanging in air, no reaction. When the match was lit, when the magnesium was lit on fire before it was put in the water, it then had sufficient energy to react. And so these particles must be pushed, energized. And that activation energy is needed for all chemical reactions. So you get wood, you have matches that exist because at that condition, sufficient activation energy doesn't exist for them to turn into carbon dioxide. and water. This means you have an opportunity to represent this graphically if you want it. That enthalpy being shown on the y-axis and just general reaction proceeding. Not really time, but not time if you wanted to think about it like time. It's not really so linear. It's more just saying the reaction starts over here and ends somewhere over here. And since we're just graphing energy, sometimes it's called a potential energy diagram, we're kind of graphing the enthalpy over the course of the reaction. So we'll make things a little bit easier. Let's talk about the magnesium reaction. Here is our initial energy. We're not really measuring time, we're just saying that's the energy of our reactants. We have a collection of magnesium and a collection of oxygen, and the way the particles are arranged, here is our reactants. And somewhere later, we have the energy associated with the magnesium oxide. The question is, how do we represent that on the graph? We know from the original videos that we watched that delta H here is negative. This is obviously an exothermic process. We release energy. Well, if enthalpy or energy is on our y-axis and the delta H is negative, we also know that that means that the final enthalpy is less than the initial, because delta means 2 minus 1 and we want to get a negative answer, so the initial has to be greater. The initial would be the reactant's energy and the final would be the product's energy. So based on all of that, we also know that our finishing point has to be somewhere down here. Now, in with that wibbly wobbly, hard to represent particle motion, we also are not putting any numbers on these axes. So this is a very, very loose interpretation of what's going on, but it is still something we use and it shows things pretty accurately. Now, to put a little bit more information on here, we can say that if let's just extend out this y-axis space such that the y-axis distance between the top and the beginning and the end would represent the change in H. On top of that, too, if the vertical distance there between the beginning and the end represents the change in H, we could probably stretch this a little bit too and say that this vertical distance for these products would be the energy of your products, right? The enthalpy of your products, and the vertical space over here would be representative of the enthalpy of your reactants. These particles, especially one where gas is a reactant, things are chaotic. Ideal gases, but KMT as a whole says that these gas particles are running all over the place and they're smacking into each other. We learned a little bit about temperature being an average kinetic energy. So really, if you have all of your particles, it's not really safe to say that there's one way to get from beginning to end. In fact, enthalpy is one of several things in chemistry we call a state function, where if we're going to calculate it, the only two numbers that matter are the beginning and the end, which is both wonderful and liberating, but also a little bit confusing. Because I don't care whether you follow a straight line to get from reactants to products, or you follow this weird pathway where things are bouncing into each other 10 times, and then you end up at products. At the end of the day, it's just the beginning and the end that we're worried about. However, we do know about this other thing called activation energy. We need to stretch some of those bonds before we can start making new bonds. It's not so simple as saying we blow apart all the atoms and then recombine them. If you want to think about it that way, that's not a terrible way to think about it. But in general, that stretching motion, that use of the match to get the reaction going, would add energy into this system. So we're going to see an increase in the energy to some point, and then all of a sudden the match wasn't needed and it was self-sustaining, and boom, all of our product is being made. So this whole thing here would be the general tracing the line of the reaction coordinate, starting here, following the pathway, and ending up down here. This is our reaction coordinate. This distance here, measured from our reactants all the way up to the highest point, let's just call that the highest point, I know, forgive my artistry, is going to be the amount of energy needed to get us to the point where the reaction is just going to keep going on its own, or it's going to complete. There's a number of ways in which these particles will arrange themselves, but there's this minimum threshold stretchiness before things snap. And we're going to call this vertical distance our activation energy. And I think that about labels everything. There is this little term down here. I guess we should talk about this. This top point where you've just about stretched everything to its limit and you're just starting to make the new bonds has some names, multiple. One of them is called the transition state, but it's also called the activated complex. And I guess that's a little confusing. Activated complex, activation energy, it's a lot. And that would be, if we wanted the energy of the transition state or the activated complex, that would be all the way down to the bottom of this graph, all the way up to the highest point. We did talk about this idea of making bonds releases energy and breaking bonds absorbs energy. So is it both? Is it neither? Because I see a line going up and a line going down. And that's really, this should really tie in to what we saw with the delta H. Up until this point on the activation of the activation energy on this potential energy diagram, this would be really where we do most of the breaking, and down here would be most of the making. Yes, it kind of all happens in a nice concerted motion, but that is typically how we look at this graph. And if you look, it is kind of clear to me that the amount of energy of the breaking is less than the amount of energy released upon making. So if making is greater than breaking, of course I'm talking about magnitudes here, so absolute value, that would be an exothermic reaction. And then, of course, in the opposite, if making is less than breaking, that would be endothermic. And so let's take a look at what that looks like. Here we have a reaction that I pulled off of table I. This is the reaction between nitrogen and oxygen to make nitrogen dioxide, poisonous brown gas. But we can draw another reaction coordinate that would show that. The biggest difference here, we have our starting point of our N2 and our O2. Since our delta H is positive, the H goes up as a result of this reaction. A lot of what I said on the previous slide is now reversed. Now we're going to end up at a higher energy than we started at. But still, there needs to be an activating step where we climb to some highest energy. There's always the activated complex, or the transition state, is always the highest point on your curve no matter what. Even if you're ending up with your products at a higher energy than what you started with, you still have to climb to yet a higher level if you're going to have this endothermic reaction occur. So we can go through and label everything we labeled before. I like to put a couple dashed lines to not be confusing about what lines are going where. Let's label everything in green. You still have your reactants and your products, and the distance between your reactants and products is still your delta H. Your activation energy is still being measured. Oh, I should change colors to not be super confusing. The activation energy is still the minimum energy to get from your reactants to the top of your curve. And so largely this looks the same. You can label all the same stuff. Really early in the year, we talked about the idea of the plasticity of the permanence of chemical reactions. A lot of times you want to say that a physical process is reversible and a chemical process is not. However, if you rip a piece of paper, it's still paper, and you can't really put it back together again. Yeah, there's tape, but that's not the same thing. Or if you crinkle a piece of paper, you can flatten it out, you can try and iron it, but it still won't quite look the same. So not all physical processes are reversible, and some chemical processes are. And so what I have here is a reaction coordinate for both an exothermic and an endothermic reaction, where I've kind of lined up the energies. It looks like the energies of the reactants of the reaction on the left and the products on the right, and the reactants of the products on the left and the reactants on the right are at pretty much the same energy. And in that case, especially in this case where the activated complex is the same, this is of course exothermic, shown by this delta E here, and this is endo. But what are the C and D but the A and B in the other direction? I almost wish this was labeled the other way. You know what? I'm going to change this to make this even clearer. You could write, since these reaction coordinates, these axes, don't really have any numbers or mean anything, you could write a reaction happening in the reverse direction. And for the reverse reaction, you could just use the same picture. Just start from the right and work your way left. This distance, if we're going in the reverse direction, this distance is our activation energy, and you'll notice over here that the activation energy is shown. So looking at these reaction coordinates, you don't have to draw it both ways as you see here. But I just wanted to put that idea out there. And if you do that, notice that I did circle the two energies, the delta E's. And I labeled one as exo and one as endo. But if you literally wrote, if you had a specific example, the reverse reaction, and that is to say, so if you started at the end and went to the beginning, the delta H would have the same value, but it would just be opposite in sign. And so now we've kind of talked about this idea of scaling up and down our reactions before. If you have multiple moles, the energy is multiplied and stoichiometric. But you can also flip a chemical reaction and negate that delta H value. I don't know when you're watching this. I mean, obviously I know a lot of you are watching this the day after I recorded it. But this is, I just wanted to take a minute. You could stop the video here if you want. But this is the loop. This is the last one before I hit something that I recorded a year ago. Which means if you are watching this in order, you're about to see the production quality and my presentation. Maybe, I don't know, take a step backwards. This might be backwards. I'm not sure. But, you know, whether you were watching this because I told you to or as part of an assignment or you're interested and you're learning from it, I just want to say thanks. I've been meaning to do this for years, and I'm happy to have made it through this portion of this journey. I mean, everything else happening out in the world notwithstanding, this is the tiniest of the silver linings. Because I have this now, and it exists, and something, like I said, I've been meaning to do it for years, and so now it's recorded and it's there. So, like I said, thanks for watching.